This is Beverly Owens, section M3 with Lab 3 constant velocity motion. We are observing a video of a moving pool ball in a straight line on a pool table, and our main result is the model gave a good prediction of the observed motion by using Newton's second law and F net is equal to 0. This is a clip of a friend hitting a pool ball across the pool table. I made sure that the positive x direction was going to the left because that is the direction that the ball is moving. I measured the diameter of the pool ball with a calibration stick, and the length of the pool ball was 0.05715 meters. I also made the point mass on the pool ball when it first began. I recorded this throughout many time intervals, which allowed a graph to be plotted to the right. The whole time frame is a little less than 1 second. It's 0.934 seconds to be exact. I also decided to start the clip after the pool ball had been in motion and ended the clip before the pool ball had stopped. To begin to predict the motion, we had to know the mass of the pool ball. I looked this up online and it was 0.156 kilograms. I entered this into VPython for the mass of the object. I also had to know the initial position of the ball. I looked at this from the tracker system, and it first began 0.098 away from the origin. To calculate the velocity of the ball, you took the final position minus the initial position all over the final time minus the initial time. The velocity therefore was 0.776. I also made sure that the timestamp for delta t was 0.001. This was due to my clip only being 1 second, or about 1 second. This allowed you to actually see the ball changing position. The predicted time for our model is less than 1 second because our video clip is only 0.93. Because velocity is constant, this means that the net force has to be 0. This makes sense because there's a mass, time, and initial velocity value. So for force to equal 0, F over m times t all has to equal 0. So I plugged in the Newton's second law equation, which would help us then get our final position. The axis of the ball, whenever it moves to the left because the origin has been changed. That to the left is positive and to the right is a negative in the x direction. You can also see on the graph that it is starting at that same value and is increasing in time and in distance away to end at the final position. I plotted the data and the predictions on the same graph to compare the model and the experiment done on this Excel spreadsheet of position versus time. The green line represents the experiment. The purple line is the model line. For our what if, this is about if the origin was changed. Our original origin was in the positive x direction, which was an increasing graph and the ball moving to the left. If we had changed this origin, it would be going to the negative x direction. Our graph would be decreasing and becoming more negative. I am changing my x positions to negative, and I make my axes so that the left is negative and the right is positive. You see that the ball is moving to the right in the negative direction and that the graph is slowly decreasing. So what does this all mean? I would think that we could make a very good educated guess to say how many pushes and pulls make a net force of 0. Just because of Newton's third law, for every action there is an equal and opposite reaction. So basically saying that there's always going to be a force against the ball and a force against the table. There can also be a normal force and a gravitational force acting on the ball as it moves.